Welcome back to this next video in which we are discussing the third isomorphism theorem. Okay, so we've now discussed the correspondence theorem, which people often view as being part of the third isomorphism theorem, or at least you need to understand that in order to understand the third isomorphism theorem. Okay, so we're now actually going to discuss the theorem which is absolutely called the third isomorphism theorem. So here it comes. So I'll just put a little title here, so I'll just call it the third iso, and then actually I'll put THM for theorem. So the third isomorphism theorem then. Again, it looks complicated when you first see it, but actually it's incredibly simple. Okay, so what we're going to have then is we're going to have exactly what we've been dealing with up to now. We're going to have some subgroup that is in between the normal subgroup that we're going to be quotienting out by and the entire group. Okay, so here's the normal subgroup, and it's of course going to be normal in our subgroup H, and H is now going to be a normal subgroup of G. Okay, so we're going to have H normal in N and N normal in H and H normal in G. Okay, so we've got this in-between subgroup that is normal. Now, from what we've just been discussing, we know that if we take the corresponding subgroup in the quotient group of G quotiented out by N, okay, so if we look at H quotiented out by N, okay, the corresponding subgroup in the quotient group, that is now going to be a normal subgroup of the quotient group. So this is going to be normal in G quotiented out by N. So now arises the interesting question: what if we were to quotient the quotient group out by this normal subgroup? Okay, so what if we were to take the quotient group here, G quotiented out by N, and quotient it out by H quotiented out by N? Okay, and the third isomorphism theorem states that what you get is going to be isomorphic to if you just took the original group capital G and quotiented it out by the larger normal subgroup capital H. So because H is a normal subgroup, you can quotient G out by it. Okay, and that there is the statement of the third isomorphism theorem, that if you quotient the quotient group out by this corresponding normal subgroup to H in the quotient group, what you get is going to be isomorphic to if you just took the group capital G and quotiented out by the subgroup capital H here in the first place. Okay, so to try and understand this better before we actually do the proof of this, let's just draw a picture and try and understand what this is saying. Okay, so we'll copy out the same picture again. So here is going to be our entire group capital G, and I think we've always been denoting the entire group in green, but I'll just verify that because I don't want to suddenly change the color code on you. So yes, I have. So we'll have G here as the entire group. Okay, like so. Okay, so I'll underline it in green there, and then we'll draw on our normal subgroup firstly, and I'll try and split it into even more cosets this time. So I'll try and split it into 8 here. Okay, so let's have the normal subgroup dividing the entire group into 8 cosets like so. Okay, so now I'll have the normal subgroup down here in orange. Okay, so that is the normal subgroup capital N here. And now what I want is some in-between subgroup capital H. Okay, now it doesn't have to be properly in between them, of course. It could be N itself or the entire group capital G, but it's a little bit boring when you do that. Okay, so let's have it properly in between for the basis of this picture. So here in pink, this is going to be our in-between subgroup, which is H here. Okay, and what we're now saying is that, okay, we can take our quotient of the group G by the normal subgroup, and of course we'll get this set of cosets with the group operation that we know how to define on that set. Okay, and now what we're saying is we can construct this subgroup of this, okay, which is the corresponding subgroup to H. Okay, so we can construct H quotiented out by N, okay, and that's just going to be these two cosets here, so that's going to be a subset of this, and it's in fact going to be a subgroup that will be normal if this was a normal subgroup of G. Okay, and what we can now do is partition the set of cosets here, okay, so the set of cosets, so we've got all 8 of these cosets now, into cosets of this. So this subset of the cosets, which is these two cosets here, we're now going to partition it up into those we're going to partition up the set of all cosets into cosets of this subset of the quotient group here. Okay, in this way we're going to quotient out by this. Okay, and what that will correspond to doing is splitting up the cosets now into cosets of this collection of cosets, this collection of two cosets here, which is h quotiented out by n. So in terms of the picture, what you'll actually be doing is splitting it up, and I don't know what colour to colour this in. Okay, I'll colour it in red, so you might get cosets that for the basis of the picture I'll show you like this. So these are the cosets now of this subgroup of the quotient group. Okay, and they're cosets that just contain two elements of the quotient group each. And now the new elements are going to be these larger cosets here. Okay, these red ones, and you're going to have 4 elements over here. And the statement is that this is actually the same thing. It's isomorphic to if you'd just taken the group and quotiented out by h, and I hope that's kind of intuitive, because if we'd just quotiented the entire group out by h, we'd have just taken the cosets of h in the first place, and look, they're intuitively going to be a similar size to that on the picture. So I know that isn't a rigorous argument, but I hope that gives you some intuition as to why this result might be true just from a picture there. Okay, so now let's actually see the rigorous proof of this. Now the proof of this isn't too complicated. Okay, we can just establish a nice homomorphism from here to here where the kernel is this, and then apply the first isomorphism theorem. Okay, so let me show you how to do this. So what we're going to have is we're going to create this homomorphism here, which is going to be a map from our quotient group of g quotiented out by n to the new quotient group here of g quotiented out by h. So remember, we're assuming now that n is a normal subgroup of g and h is a normal subgroup of g, but h is the bigger normal subgroup of g. It's the one that completely contains n. So I'm now going to have a map from the cosets here to the cosets of h here. Okay, now how is this map actually going to work? Well, it's going to take any coset which is a coset here, and we need to have colour coding now. Okay, so I'm going to colour code everything to do with the quotient group of g by n in yellow here. So this coset here, the coset that contains A is an element of the original group, and this is a coset in the partition of the group up into the cosets of the normal subgroup n here. Okay, so that's why I'm going to colour the bar here in yellow, because it's a coset in this partition here. Okay, and I'm just going to map this onto the coset that A is contained in, but this time in the partition for this one, and I'll colour this one's partition in red. Okay, so we can also partition the group up into the cosets of H here. Okay, and now I'm just going to say that I'm going to map any coset here onto the coset that it's contained in this partition. Okay, so the first thing I need to do is explain why that is a well-defined map. So actually drawing a little picture here is probably quite helpful. So I'll draw the two separate partitions on these separate diagrams. Okay, so I'll try and make it a little version of this picture here. So I'll partition the group up into 8 pieces here for the partition that we do when we quotient out by n. Okay, so these are the cosets, if you like, of yellow, so I'll just circle the entire thing in yellow here. So these are the cosets that we get when we partition up by this normal subgroup n here, so I'll just colour that in orange there. And now what we've got over here is we've got the group partitioned up into the cosets of H this time, so this is the red partition here, like so. Okay, and I'll just mark on H as well, so we have H previously represented in pink, so I'll stick to that. So here is H, and H completely contains N, as we know. Okay, right, so how then does this mapping work? Well, it's taking any coset in here, okay, so a coset that contains an element A, so let's say we've got some coset, and I'll just colour it in, so we'll have it coloured in purple here. So here's some coset under this partition here in this quotient group. And what are we mapping it onto? Well, we're saying, okay, this contains some representative A, find whichever coset over here contains A, okay, and as far as the picture is concerned, it'll be this one here, and then that's the coset that I want this coset to be mapped onto. So this coset is A bar, but the coset under this partition containing A, and I'm just going to map this coset onto here. So the first thing I need to do is make sure that this is well defined, okay, because of course this is a map from a set of cosets onto a set of cosets, okay. I need to make sure that it does not matter which representative of this coset that I look at, because there is a potential here that this could be very, very bad, okay, because when I'm trying to decide which coset over here this coset will go onto, I have to find a representative of here, take whatever representative you like, and then you have to say, okay, which coset over here is that representative contained in, and then I'll map this coset onto that coset. Okay, but what if it's the case that different representatives from this coset are in different cosets over here? Then of course this wouldn't be well defined, but I do need to start off by checking that this mapping is well defined. Okay, right, so I need to show that whatever element of this coset that I take, they will all be in the same coset over here. Okay, so all the things in this coset of A are of the form A composed with n, where n is an element of the normal subgroup n here. Okay, so remember, a coset, you can either view it as a left coset or a right coset. I always prefer to work with left cosets, which is why I've put A on the left here, but you could put it on the right. Okay, if you want to construct all the things that are going to be in this coset of A here, all you need to do is just compose A with all of the elements of the normal subgroup capital N. That will give you all of the elements in this coset. Now, if we think about what all the elements of this coset are going to be, they're going to be A composed with all of the elements of the larger subgroup capital H, and we know that the entire subgroup capital N is contained within the subgroup capital H. Okay, so in fact all of the elements over here are actually going to be in this coset of A over here. So indeed, I hope you appreciate that whatever representative you take here, you're always going to get this coset being mapped onto the same coset over here. So indeed this mapping is well defined. All of these elements that are in the same coset over here are going to be in the same coset over here, basically. Okay, now what might be the case is that lots of different cosets here are going to be mapped onto the same coset here. In terms of our picture here, this coset in purple and the one below it will be mapped onto the same coset over here, so this isn't necessarily an injective map, okay, if indeed this subgroup capital H is larger than N, it's not going to be an injective map at all. Okay, right, so that's the way I'm going to define this map. Now what I want to show you is that in fact it's a surjective homomorphism, I do apologise, group homomorphism, forget what I just said, group homomorphism, you might not even have seen the definition of a ring yet. Okay, I want to show that it is a surjective group homomorphism. Okay, right, so I need to show that it obeys the homomorphism criterion, okay, which is that the composition laws are compatible between the two. Okay, composition in here is compatible with composition in here. So I need to prove that phi of any two cosets in here composed together, so I'll have the coset containing A composed with the coset containing B here. Okay, so this is a coset in here, this is a coset in here, and they're composed currently in there. Okay, and then I work this out, this will be some coset in here. Take phi of this, that'll give me some coset over here. Okay, I want to show that the answer I get is the same as if I firstly mapped the coset A bar into here, so mapped A and got a coset here, and then composed it in here with phi of B bar. Okay, so let me colour these in red. Oh, whoops, no, sorry, forget that. That one, the composition is in red, but these are still cosets in this original one here at the moment. Okay, right, so this is what I want to prove is true. This is that the composition is going to be compatible between the two. Okay, this is what I need to show, obviously, to show that this is a group homomorphism. Okay, right, so how are we going to do this? Well, we'll just work on both sides and try and show that they're equal to one another. So let's start with the left-hand side here. If I want to compose the coset containing A with the coset containing B in this quotient group here, everything's in yellow. How do I do that? Well, I take a representative from here, a representative from here, compose them together in the initial group, and then take the coset that contains that. So this is going to become A composed with B bar. Okay, so where A and B are now composed together in the initial group. So I just took as my representatives A from here and B from here, sensible representatives, got some answer in the group capital G, and then just took the coset, and that's the yellow coset, so I should have a yellow bar there, okay, and that's the answer to A bar composed with B bar. And I still now need to take phi of that. Now, though, I can just apply the definition of phi, okay, because phi, I know what it's going to map any coset onto. So this is the coset that contains A composed with B. It's just going to map it onto the coset that contains A composed with B, where this is now a coset in the red quotient group here. So this is a red coset, okay, like so. Okay, so we'll drop working on the left-hand side for a while and work on the right-hand side. So let's now work on the right-hand side here. Okay, so phi of A bar, again, just apply the definition. This is A bar, but where the coset is red now, the coset under this quotienting here. And then we want to compose this with B bar, okay, so phi of B bar here. Again, you just change the bar to red here. It's now the coset that contains B under the red partition. Okay, but how do you compose these two together? Well, this again is just a quotient group. So how do you do it? You take a representative from here, we might as well take A. You take a representative from here, we might as well take B. You compose them together in the initial group, which is green composition, and then take the coset that contains the answer, and you'll want the red coset. So indeed, this is equal to this. So we can indeed tick this as being true. The homomorphism criterion is true. Composition is compatible between these two quotient groups here. Excellent. Now the other thing I want to add on to this is that it's a surjective homomorphism. It's a surjective group homomorphism. I already said that it's not necessarily going to be injective, unless you're doing a very boring example where H is actually equal to the normal subgroup. It's not going to be an injective group homomorphism, but it is at least going to be surjective. So it's not going to be an isomorphism, but it is going to be a surjective group homomorphism. Now, why can I say it's a surjective group homomorphism? Well, to be surjective, it has to be the case that every coset here has a coset here, at least one coset here coming onto it, okay, being mapped onto it. Now, why is that going to be the case? Well, if you look at any coset here, it will have an element in. So take an arbitrary coset here, let's say A bar, it will have an element in. That element has to be in a coset over here, okay, and that coset will of course be mapped onto this one by this mapping phi. Okay, so it's a bit of a trivial argument here, but it is important still to argue that. Okay, any coset here has to have something in here, because any coset here has elements in it, and those elements must have been in a coset here, and those cosets here are going to be mapped onto the coset here by this mapping. So it is going to be a surjective group homomorphism. Now, how then are we going to use this to prove the third isomorphism theorem? Well, now all we need is the first isomorphism theorem. So the first isomorphism theorem says that whenever you've got a group homomorphism, you can say that if you take the domain group and quotient it out by the kernel of the group homomorphism, then it's isomorphic to the image of the group homomorphism. And of course the image in this case is just the codomain, because we're talking about a surjective group homomorphism. So now all that remains to ask is, what is the kernel of this group homomorphism, which we know of course will be a normal subgroup of our domain group here. Okay, well the kernel is going to be all of the cosets here that are mapped onto the identity coset over here, but the identity coset is just H. So which cosets here are going to be mapped onto H? Well, of course, that's the cosets in H quotiented out by N. Okay, so my claim is that the kernel of this group homomorphism is the normal subgroup H quotiented out by N, which is going to be a normal subgroup of G quotiented out by N, because of course this is the corresponding subgroup of here for this normal subgroup in G that completely contains N. Okay, so now by the first isomorphism theorem, if we quotient the domain group, which is this quotient group, out by the kernel, which is H quotiented out by N, it's going to be isomorphic to the image of the group homomorphism, but because it's a surjective group homomorphism, that is G quotiented out by H. So there, indeed, that is exactly the formula of the third isomorphism theorem. Okay, so what this tells us, in fact, is that you do not actually get any new fantastic thing to study by quotienting out quotient groups. Okay, in fact, what you will end up, whenever you take a quotient group and quotient it further by a normal subgroup in that, it's equivalent to just finding a larger normal subgroup that completely contains the original normal subgroup that you quotiented out by, and quotienting your original group out by that. Okay, so there's no new fascinating thing to look for in quotienting out quotient groups. Okay, it's just equivalent to quotienting out the original group by a larger normal subgroup. Okay, so it simplifies things hugely, the third isomorphism theorem. Okay, so with that then, we will finish this video on the third isomorphism theorem.